In this demo, I will show you a typical mistake when you let the service or an application generate GUID IDs, but forget to remove the clustered index in the underlying SQL Server database. What did I just say? This is the domain model I will use. This class is modeling a book in a bookstore application, and it has a GUID ID. GUIDs have gained popularity over the auto-increment IDs in distributed applications. It doesn't matter which node generates the ID value, whether it is a database or any application node, a service, whatever, there will never be collisions. But there is a hidden issue if you want to take control over generating the GUID values in the application. I will show you the mistake itself, I will make it here, and then I will show you the steps you should apply to correct it when that happens to you. This application is using Entity Framework Core with database-generated GUID values. I know it is generated in the database from this detail here. When you zero out a key, Entity Framework will let the database fill it in and communicate it back when inserting a new object. From now on, the application is responsible for assigning this key. EF Core will adapt, this will work like a charm, and it will cause a nasty non-functional bug. Let me show you. This is how I have configured the book entity in the EF Core DB context. Actually, this is what GitHub Copilot suggested me to do, and I accepted it. This configuration makes sense. Let me explain it to you. I'm instructing EF Core to let the database generate value on add, and the database will generate the ID value when empty. That is the point, when empty. If the application has set the identity, as I have just started doing over there, it would be as if I had this instruction commented out. And, as I pointed out, that will be the bug. I will now show you the database so that you can see the issue. This is the SQL Server database managed by Entity Framework Core. However, this issue would be there with or without EF Core. It is not the issue when using EF Core. This, what I'm going to show you, is how SQL Server works, no matter how you use it, through which library you use it. There are two columns in the book table. The primary key is non-nullable unique identifier type. We knew that from the model I have shown you in the application. But what was not visible from the C# code, though, is the primary key index, which is clustered. It is a usual practice when using SQL Server to create a clustered index on the primary key. It saves a lot of work to the database when inserting new rows, provided that the values of the key are coming in the strictly growing ascending order. And guess what? While I had that GUID empty in my code, the SQL Server did generate GUIDs in the growing sequence. That is how it works. These are the actual values of the new IDs I got when I inserted a bunch of new books before changing my code. You may say, hey, this looks random to me, but no, these are sorted. GUID is segmented. And this segment here is indicating the time sequence, and you can witness that the SQL Server has generated that in ascending order. Then I switched to application-generated GUIDs, and these are the values I got next. Well, that is random indeed. Now is the last time for you to understand how clustered indexes work. Unlike some other databases, most notably Oracle, SQL Server is inserting new rows by appending them at the end of the table. That is why SQL Server defaults to inserting keys in the growing order, because it can build a table with no index on the key column anywhere outside the table. You see, the table is already sorted by the key. The table itself becomes its own index on the key. That makes inserting in SQL Server super fast, but only when the keys are taken from an ascending the growing sequence. If you fail on that, if the key values are coming out of order, then inserting a new row will cause relocation of a great number of existing rows to make room for one row in the middle with an out-of-order key value. Well, that is slow. As your table grows large, that will make its performance diminish to a halt. The problem with the bug I have made is that it will only manifest after my database becomes large, and then I will have huge problems to fix the issue because there will be a lot of data to move. And so we conclude that this default entity configuration is not such a bright idea. We must give up a clustered index. But it has been here for a long time and I have already accumulated a lot of data in my database, so removing an index will not be that easy. The first step is to reconfigure the key. We must tell Entity Framework that the key is not clustered. You do it this way. Here is the migration that Entity Framework has generated for that new configuration. It looks scary with this drop primary key call, but it is not that dramatic. It will not drop the column as one might think from the name of this method. It will just tell the SQL Server to stop treating that column as a clustered index, as an index in general. The next call will create a new non-clustered index on the ID column. Let's apply this migration. Blast, I've got an error. It says I cannot drop the primary key constraint because some foreign key is using it. It even gives me the name of that foreign key. So I look into the previous migrations, and that is true. Here is the earlier migration which has established the foreign key in another table that depends on the books table. So it turns out that I cannot make changes, the structural changes, on the primary key on my table because other tables are referencing it. That's what I meant when I was talking about how much data there are in the database. There are also tables, entire tables that are referencing the books key, and I cannot just change it. I need to drop all other foreign keys, then make the change to the books ID column, and then establish those foreign keys again. And I must do that in a transaction. I don't want to stay with an inconsistent database after modifying its schema. That requires you to know a lot about how relational databases work. So, this is the idea. You would drop the foreign key and then do whatever you do to change the books table, and then add the foreign key back. Now, since there will be multiple foreign keys to drop and add, I will add a utility method to drop all of them at once, and another one to add them back. This migration will work because all previous migrations have followed the same naming scheme for foreign key indexes. I have checked that in my code in previous migrations, and I can tell that these utility methods will work fine in this migration. Instead of just this one, I will drop 3 foreign keys and then add them back at the end. But that is not all. I must repeat the process in the rollback migration. In case that I change my mind and want to reinstitute the clustered index back in the books table, I must drop all those foreign keys again, then add the clustered index to the books table, and then add the foreign keys back once more. The moment of truth. I'm applying the migration. It is successful this time, but look what it had to do. It has dropped 1, 2, 3 foreign key constraints before dropping the primary key constraint and adding the new one, this time non-clustered, see it here. Then it adds those same 3 foreign key constraints back. Now, adding these foreign keys again will cause the database to verify the values it finds in the foreign key values. So it will verify the consistency of the database before completing the script. And this script is executed within a transaction. So the point is that once you run this migration, it will either do it all or do nothing of it. It will roll back. That is very important because the database was consistent before the migration, thanks to the foreign key constraints which have guaranteed the consistency of foreign key values, and it will be consistent again after the migration. That is very important to know. Again, it has nothing to do with Entity Framework and EF migrations. I would have to do all this myself if I used any other technology to manage migrations in the database. Even if I did it by hand, I would have to do all this myself. It has nothing to do with Entity Framework Core. A quick check on the database will reveal that we have removed the previous performance issue. Here the primary key is non-clustered. We can now generate key values in the application if that is what we wanted. The database will accept my GUID values, those I generate in the application, and there will be no drop in performance as the size of the table grows. Problem solved. Now, before the end, let me show you what you need to do when creating new entities to avoid this issue altogether. You don't want to make this bug I made. So far, I have been showing you what to do when you discover the issue, when you discover it late, and you figure out that there is a problem after you see a drop in your database's performance. But you don't have to make that problem, you see. This is a new entity in the domain, a publisher of the book. It also comes with a GUID ID created by the application. Now I'm doing that on the outset. I'm generating the GUID value right away. I'm not going to let the database do it for me. I will add an optional nullable publisher ID to the book model and move straight to the DB context. I want to show you the configuration. Quickly add a DB set and move to the configuration where I made the bug the last time I was here. The first step is to declare the primary key with a non-clustered index. If there is any chance that you will be generating GUID's ID values in the application now or in the future, then doing this step is essential. That will prevent the creation of the clustered index in the database, and so you will be free to generate the GUIDs yourself. Then we set up the foreign key from books to publishers, and we are done. I cannot stress enough that these complications I'm sustaining are not the result of using Entity Framework Core. If you used any other toolset or library to manage the relational database migrations, you would have to do all these steps in that technology as well. It's not Entity Framework, it is SQL Server. This is how it works. Here's the new migration. There's quite a lot of code here. Observe how the publishers table has a non-clustered primary key at the outset. That's what I wanted. Then comes the creation of the index and the foreign key. All the mandatory moving parts are here. The key takeaway from this demonstration is that this is the way for you to create GUID ID columns, so to keep the database table performant no matter who generates the GUID values, whether the database or the application. Both options are open for you now, and the table will work fine in both cases. If you forget to do it now, and it turns out that you have made damage by generating your own GUIDs, then correcting the issue will take time and effort, and you will have to do it very carefully. You have seen in this demo how to do that step by step. Otherwise, I hope you will avoid making that mistake and that your database tables with GUID IDs will be performant all the time.